yeah, well, we start with an observation, which in certain sense is trivial. There's nature is all almost the system. You can see around us there are a lot of different bodies, and the boundaries between one body and another body create problems if you want to interact. So you can see here. Well, the first feature is fiber optics. Second feature we have rupture or motion in a collinear flow, compression, force. And so one can ask, you can ask yourself what kind of mathematical model you can use for this kind of situations. This was moved, or infinite derivatives in infinitesimal intervals. Can we use differential equation or not? Calculus evaluation is it possible since we have similarities and so on. So I would like to start with a couple of citations which are also used, we can say, in the next slide. The first is from Laugwitz, the biggest expert in PDE. He told that in one of his books that the differential calculus one encounters immediately the unpleasant fact that not every function is differentiable. The purpose of distribution theory is to remedy this flaw. Indeed, the space of distribution is essentially the smallest extension of the space of continuous function, where differentiability is always well defined. So this kind of problem is also inside advance. And the second problem is also related to our previous idea to take infinite derivatives in infinitesimal intervals. In fact, if you look at this citation from Arnold, he told that nowadays when teaching analysis is not very popular to talk about infinitesimal quantities. Consequently, present-day students are not fully common to this language. Nevertheless, it is necessary to have common of it. You can see, we will talk a little bit about this later, and you can see some kind of freedom, Grothendieck freedom for the peers in Arnold's point of view, because you know, infinitesimal and infinite quantities are completely branched from mathematics. But in case of Arnold, it's not exactly independence from freedom from the peers. So we start from, once again, from this idea of the smallest extension, which is not perfectly formalized by Hörmander. By saying that, and if you know anything about distribution theory, this is in only one slide, it's a possible definition not definition, characterization of distributions. So the spaceless part distribution is a co-universal solution. Co-universal, I mean the unique error start from the solution of the following problem. You have a sheaf or real vector spaces. You have an embedding of continuous function because we want to take derivatives of every continuous function. These derivatives are compatible with. Sorry, what is the pointer? Sorry, Olivia, what is the pointer? Derivative is compatible with partial derivative. That is, if you take functions which are differentiable with continuity with respect to the variable sk, you can take the inclusion continuous fraction and back in the distribution and take the distributional derivative, or you can take the classical derivative and that is the embedding, and you get, of course, the same results. Here is an important condition about when you have that derivative, distributional derivative of continuous function is zero. This happens if you are in this dimensional interval. If f is the sum of polynomial in xk, which one of degree less than alpha k, alpha is not index here, and the whole coefficient are independent from xk, and the derivative commutes. This is you can take this as I have a sheaf satisfying this property and these are the solution. And with this I can take any derivative of any continuous function. Okay, and this characterizes the sheaf, the whole sheaf of distribution up to S. And then you can even take this is the idea of Sebastian and Simon, even if it has been completely forgotten, more or less. Is you can take this idea to define that derivative of I think it is very interesting because in this way you have a completely algebraic definition, isomorphic sheaf of distribution without any tools from functional analysis. Absolutely nothing. Okay? What are the problems with Schwartz distributions? Schwartz distributions are not functions. Even if engineers, physicists use this kind of function as some kind of function, etc. Maps. Each has a function, is 0 for x less than 0 and 1 for x greater than 0. Delta is the derivative of each. They are not functions. So they are very good for linear problems, but not for nonlinear ones. This kind of calculation are very well known by every physicist. For example, if you admit that you have the Leibniz rule, then you have this equality and this one, but h takes only values 0 and 1. So the pointless product gives this. So from this and this one, you have a 2h prime here. Here is equal to h prime, so equal to 3h prime. So you get h prime is equal to 0. So from this once again, 2h prime equals h prime, so that is 0. So you don't have anything here after that. And indeed, well, okay. I talked at several conferences with physicists that told me, we know this kind of calculus, but we don't know how to solve it. Okay, about that. And indeed, you have the Schwartz possibility theorem. There does not exist a differential algebra embedding distributions where these linear operators and distribution derivative satisfy the Leibniz rule, and where the product is the distinction of the pointwise product of continuous functions. Okay? You cannot take composition, and so they do not form a category, even have delta square, okay, because you don't have a meaning for linear operation. So you cannot even state the nonlinear or the differential quotient differential equations. And even if for linear or the differential equation, you cannot even forbid the initial variable, because this point was the correlation doesn't have any meaning. Okay? So if you want to solve this kind of problems, you have to think that more or less. Of course, there are several solutions around it, but a lot of people are stuck in this kind of problems. So you have to take this freedom from peers point of view. Okay, so I listed here a very few list of biases that you can find in Wikipedia, and for example, the conservative bias, the tendency to simply revise one's belief when presented with new evidence, okay, or the low instruments, the over-reliance on familiar tool methods, ignoring or undervaluing alternative approaches. Okay, these are well-known cognitive biases in mathematics. I only underscore a little bit two, which I think we can experience every day in mathematics. And I think they are related to Grothendieck point of view. My point of view, Grothendieck philosophy and some kind of, and also the relationship with religion are at least as important as it is mathematics. My point of view, more important. And so if you want to solve some kind of problem, Grothendieck said if you want to be creative, you need some kind of freedom from your peers. Okay? Even if at the same time, Grothendieck said, but at the same time you have to accept your solitude. Okay, because if you are free from your peers, okay. So these are a couple of pictures you can take from a website, a very famous university, of course. This is the XH function. This dot is a problem. This is some kind of picture, more or less, of the direct delta. Okay, and this formula is informal formula very well used for distribution, and indeed the generalized function after Schwartz and first fits better. Okay, wonderful work and wonderful person. They are functionals, they are not functional. They are functional defined on the space of completely supported Zambon functions, combination of etc. Right? And there are some kind of they satisfy some kind of continuity. Okay. On the other hand, it's very interesting. If you look at the original work of Cauchy, Poisson, Kirchhoff, Helmholtz, and so on, Hellesat, even before Dirac, you will see that they already use some kind of generalized function. But they are smooth theoretical maps obtained from ordinary smooth maps by introducing simple infinitesimal or infinite parameters. Even, of course, the Rieger scalar for this classical author was completely informal. They don't even know what are real numbers. Okay? At least not at our level. So, for example, if you take an invertible infinitesimal sigma as a standard deviation in Gaussian density, you obtain a delta function. You can see this kind of calculations and delta properties in Cauchy works, not in Dirac or either side. Okay, not with the Gaussian with another. But if you want to formalize it as a second point of view, you need, so we return back to Arnold, you need infinitesimal infinite numbers, and so you need to extend your Rieger scalar into new Rieger, not Rieger, because it contains infinitesimal numbers. And so, but we don't have to talk about abstract filter, standard analysis, or synthetic differential geometry, something like that. There is an even more simple approach. So first of all, basic notation I will be the interval 0, 1 open on the left. Epsilon will be always the variables for any point here, 0, 1. And any function defined in I, the point was evaluation will be denoted with the subscript. Okay? So the whole theory depends on a fixed infinitesimal function, net, which is called the gauge. And we will write for epsilon sufficient as model property B holds if for epsilon sufficient as model property B holds. Okay? Yeah, I will pronounce epsilon, C, phi, and so on at Greek pronunciation, but at least I will try and with the American one. So we have first to introduce the class, what was algebra of Roman rate nets function, which is denoted in this way, and which are functions that for epsilon more are, you cannot take any infinite net, but at most nets of this form, for epsilon to minus n, if they are infinite. Okay, these are called Roman rate. Then introduce the notion of negligibility, non-isolation, saying that two nets are equivalent if their distance is less than any power of your gauge, right? And this quotient ring is called the Robinson-Colombeau ring of generalized number, and the equivalence classes in this quotient ring will be denoted simply by square brackets. This is the symbol for your ring. You can define another relation, saying that the first number x is less than the second one. If you can define, you can find another representative for the second one, such that this pointless relation works. For epsilon. Very important. We say that x is strictly less than y, saying that x is less than or equal to y, but the difference is invertible. So not x is different, no y, but the difference is invertible. And we can define the absolute value of generalized number as the generalized number generated by the absolute value. This seems a trivial step, but this means that you are defining a metric which is valid in your new Rieger scalar. So you are saying, I want to change my Rieger scalar from R to this particular word. Okay, and this is not a trivial step. Indeed, there is a lot of research where they try to define a metric as you should, so with values in R, the real thing. Okay, so this seems trivial, but it's not a trivial step. This will be the notation for the generalized number generated by the gauge itself. So it is infinitesimal, positive vertical infinitesimal. Very interesting. We can define intrinsically what is infinitesimal. It is a generalized number which is less than any absolute value than any real number. And this is completely equivalent to see that take n represented and the limit is here. So you have a complete dialogue between standard analysis and your new name. This equivalence relation does not hold in non-standard analysis. Okay? And the same for infinite numbers. So using this strict order relation, you can radii, sorry. And this generated topology, which is called the short topology. And actually, the topology is generated by infinitesimal radii. For example, the form you go rise to Q power. Okay, this has several consequences. So, what is the intuitive interpretation of this kind of general number? You can think of that as the variable epsilon as some kind of time, epsilon time. So, epsilon going to 0 means eventually for this epsilon time sufficiently far. Okay, and so you can see in the previous definition we didn't introduce any limitation about regularity in epsilon. So epsilon is a completely arbitrary maps with respect to epsilon. So you have static point that does not depend on epsilon, and these are real numbers, and you have some kind of dynamic points. So these dynamic points can also jump. You can have discontinuity, and the black path you can see here is a possible representative. Around this path you have some kind of fuzzy halo of negligibility distance, because two representatives are equivalent if their distance is less than any power of the gauge. So, for example, as a distance of the form of epsilon to 1 over epsilon. Why arbitrary representative? Because this is necessary. We have several counterexamples who have classical theorems for generalized function, like intermediate value theorem, mean value theorem, and so on. Okay? So we introduced the ball with radius generalized number r and center c, and you can think that they are generated by the Euclidean ball. This E here means Euclidean ball in the ordinal Rn, where you have that the radius, both the radius and the center are dynamic numbers. Okay? So similarly, you can define two kinds of interesting sets of generalized number. The first, so you start from an arbitrary net of subset of Rn. Then first define an internal set, which is denoted with this brackets, is the set of generalized numbers, such that for at least one, okay, but at least one representative lies in A epsilon for epsilon sufficiently small. We will. And these are always closed in the short topology. And then strongly internal set, denoted with these Japanese brackets, the set of all generalized numbers, such that they remain always at an infinitesimal distance, depending on the point, from the boundary of the net. This means it is possible to prove that if you, for some representative, you are in A epsilon, then for all other representatives, you are still in A epsilon. Okay? So this is an intuitive representation of an arbitrary ball. So you can have that the center is moving in epsilon, the radius is stretching or enlarging, and the center can jump and so on. And this is a picture of internal set, the closed, and indeed the closure in the short topology of the ball is the internal set generated by the net of closed Euclidean balls. And you can see you can have some representatives which are inside this Euclidean balls, but some other representatives which are outside for a negligible distance. And on the other hand, these are strongly internal set, that is, they are always at a certain positive distance, infinitesimal distance from the boundary. So you have this property does not depend on the representatives. So in only one slide, we can define what are generalized functions in these settings, and following the idea of the classical author. And the idea is exactly if you set an infinitesimal, and now we have a meaning for this infinitesimal, sigma, in a Gaussian density, what you get a net of smooth function. And so, taking an arbitrary set X of generalized number as a domain and Y for the codomain, you say that f from X to Y is a generalized smooth function, denoted also in this way. F is a map from X to Y, so you set theoretical function. So So we return back to the use of classical author and also of informal use of physicists, engineers, and so on. And there exists a net of smooth function, like in the case of the Gaussian, that defines these theoretical maps, in the sense that they are defined in some omega epsilon. The strongly internal set generated by omega epsilon contains the domain X, and the values of the function f are what are exactly are the generalized number generated by f epsilon evaluated at x epsilon for every representative x epsilon. And very important, we want to take any kind of any order of derivatives. So whenever you take a derivative, you are still in your ring of scalar. Okay, so you get a rho moderate. So at most an infinite of the form rho epsilon to the minus some power. Equivalently here, we can use the partition of unity instead of omega epsilon. We can take a function, define the whole space, and it's also interesting that, well, I've forgotten to tell you, both the ring of, formally stated, the ring of Robinson-Colombeau is the simplest quotient ring where you have non-trivial quotient ring, where you have that infinitesimal, or better, representative of 0 are infinitesimal in the standard set. That is, any representative goes to 0. Okay? The relation that does not hold in a standard net. And similarly here, you can prove this universal property, that is any other way to get maps using nets of smooth function is smaller. So one can see, oh my God, this is a ring, and it's not a field. We don't have a total order property. We don't have existence of supremum and infimum, so it's a nightmare. So to convince you that it's not a nightmare, I listed here a list, of results. And you can see this as a kind of Grothendieck Rising C methods. That is, we started to develop this theory thinking to develop a beautiful theory. And at the end, of course, we started from a certain group of people working in similar topics, which is the community of Colombeau generalized function. So Schwartz function and embedding as smooth function are completely preserved. Generalized function are freely closed with respect to composition, so they form a category. So you can consider delta composed with delta or whatever you want. You have one-dimensional integration, all the classical theorem, and stated in a very natural way. You have multi-dimensional integration with very good limit properties. You have a theory of ordinary or partial differential equations with the Picard-Lindelöf theorem for PDE, and the Mondovì, but with infinitesimal intervals and infinitesimal dependence on the parameters, so you need a non-Archimedean language. We have calculus of variations, hyperfinite Fourier transform, that is, we can define, we have a Fourier transform with essentially all the classical properties for all the generalized smooth function, not only of temporal type. So we can take the Fourier transform of the exponential. It's not a problem. And it is a completely non-Archimedean function. At every finite point, it takes as values an infinite number. Okay? So once again, you need this language. And recently we also defined generalized holomorphic functions. So we can also extend, for example, any compactly supported function, for example, Dirac delta from the real fields to the complex field. Okay? And the Dirac delta is a holomorphic function. So on the other hand, not all properties can be, we return back to important Grothendieck Rising C method, that is thinking at beauty and searching for the beauty. You have something that is growing, and you hope that several problems can be solved simply in this setting. Okay. Of course, on the other hand, not all properties can be preserved. You can see here some properties. For example, you recall that the sharp topology is generated by balls with infinitesimal radius. So think of two different real numbers, put a ball on one and on the other, and you have that the sharp topology induces the discrete topology. But on the other hand, of course, with respect to the sharp topology, generalized functions are continuous. And indeed, this is a correct picture of the Heaviside function. these are infinitesimal oscillation. This is an infinite derivative, okay? So if you take even a finite interval on the y-axis and you take the counter image of under this function, you get an infinitesimal interval. If you want to have continuous function for this kind of generalized function, you must have infinitesimal neighborhood, and so you must have discrete topology on R, okay? Infinitesimal are Klopen, and so any interval is not connected. And you can say, oh my God, it's a nightmare. Intervals are not connected. Okay, but on the other hand, exactly because you have that intervals are not connected, the identity theorem for analytic function does not hold. That holds only with some sufficient conditions. And this is, as a consequence of this is that the Dirac delta is analytic, even if it's completely zero for x is sufficiently large, but not zero around the origin, infinitesimal the origin. It is exactly because you have Klopen set, okay? Supreme and infimum does not exist, for example, not in general, for intervals, of course, these are A and B, but for the set of all infinitesimal, supreme and infimum does not exist, and this is sometimes a problem. But every non-Archimedean theorem has similar problems, okay? So under this, there are some kind of impossibility theorem. So a couple of words before talking about topos, about the physical modeling and this kind of generalized function. Also, Marsden tried this kind of formalization using Schwartz distributions and published 2 papers, but unfortunately in the first one of this, there is an important mistake, and so essentially no one was able to develop this using Schwartz distributions. So this is an example to say the dynamics of the bodies in our real worlds actually are not C2. The classical assumption of mechanics are a little with some kind of singularities. So this is the length of this pendulum wrapping around this parallelepiped. You can see this is the Heaviside function. You can see here a nonlinear operation. This is a generalized function, and this is an infinite number. So you can argue saying, okay, but infinite quantities are not possible in physics. I read this a lot of times. I think this is epistemologically wrong because we are not modeling what happened at singularities. Okay, here we have a strong nonlinear behavior, and we are not introducing new physical ideas about what happened at the singularity. We model what happened in the infinitesimal time before the singularity and after the singularity. Okay, so we are still inside the classical mechanics. Someone said, oh, you have infinite speed, so you must use relativity theory. No, my God, please not. Okay, we are still inside classical mechanics. John von Neumann, reasonably wide area. So we consider physical systems where the duration of the singularity is negligible with respect to the duration of the other phenomena that take place in the system. So the duration of the singularity is infinitesimal. This means that, for example, you must have infinite derivatives, okay? Which means they are derivatives larger than any other quantity you have in your system, not actually infinite. This is the equation you can get for the systems using the Lagrange equation. You can see a lot of nonlinear operation with theta and with lambda. So it's impossible even to formulate this equation for Schwartz distribution. So we constructed several models for Lagrangians in optics or for quantum mechanics. We have a formalization of the uncertainty principle with the Dirac delta, motion between 2 different media. This is the behavior of still linear and then nonlinear and then the rupture, collision between different materials so that to reproduce the coefficient of restitution, the speed before and the speed after the collision and so on. Okay, but now we start talking about sheaf property and topos theory for this kind of generalized function. We start with a counterexample, a classical counterexample in non-Archimedean analysis, which is this function. you can define this function saying that it is equal to 1 if x is infinitesimal and equal to 0 otherwise. The domain of this function is the disjoint union of the sharply open set of all the infinitesimal, which is Klopen, I recall, and its complement. So you have a not beautiful situation, that is I restricted to an open set is 1, and I restricted to the complementary of this open set, which is still open, is 0. And both of course 0 and 1 are wonderful functions, they're a constant function. On the other hand, I is not a generalized function because it doesn't satisfy the intermediate value theorem. It takes only 2 values. Okay? And indeed, the generalized functions are not a sheaf with respect to the sharp topology. They are actually a sheaf with respect to ordinary Euclidean set, open Euclidean set in Rn. But we are not so interested in this property because we want to have a sheaf property with respect to the set, open set in the sharp topology of generalized number, okay, not of standard numbers. Therefore, in order to get a beautiful theory, it does not suffice to consider sharply open set a generalized function because they are not a sheaf, and we have to use another way. In the following S, G, C infinity is the category of strongly internal set and the generalized function. So we first introduce what is a functionally compact set. If you consider compact set with respect to the sharp topology, they are completely trivial. So you have to introduce what is compact set for this kind of generalized function. And this is a very good definition. A functionally compact set, denoted in this way, with this F here, is essentially a closed and bounded set in this setting. So it is an internal set, the set of all the generalized numbers such that at least one representative is in K epsilon. This is always closed in the sharp topology. They are bounded, but with respect to our new ring of scalar. So the ring of scalar can also be an infinite number, but bounded with respect to this ring of scalar. And this K epsilon is a net of ordinary compact set. So they are bounded, closed, and defined by ordinary compact set. What is the good point? Is that our generalized function believes that this kind of function, even if they can be infinite, like this interval, which goes from 1 minus infinite to a plus infinite, they believe that these are compact set. Indeed, the image of functionally compact set is a functionally compact set, and most important, generalized function always satisfy the extreme value theorem on functionally compact set. So they take minimum and maximum, even if these are completely unbounded from the classical point of view. For example, if you take the row, so this infinite number, negative, this positive number, infinite number, positive, and this contains all the classical static finite number. And generalized function takes maximum, minimum, maximum in this interval. This is the classical mimicking of the usual definition. We say that X admits a functionally compact exhaustion if there exists a net, a sequence of functionally compact set, one contains in the interior of the other, such that the union is, gives the whole X. Okay. So to introduce the correct sheaf property for this generalized function, we have to introduce a new compatibility condition, which is called dynamic compatibility condition. And the idea is that for epsilon that going to 0, this time that is moving, you can move from one index set to the other, okay, freely. So we introduce, if J is some kind of index set, we introduce the set of all the functions from I to J, denoted with the square brackets. And then we say if we have a set theoretical map, a functionally compact set K, such that when you take this illustration, you get a generalized function on this set. Then we say that this net, this family, indexed in J, satisfies the dynamic compatibility condition on this cover K of K if there exists a net epsilon smooth function that defines Fj, such that, this is the first point, here we have Uj as a covering, but here we allow that J epsilon, so you are moving from one index set to the other, J1, J2, as epsilon going to 0, completely free. and you get this strongly internal set generated by this new net. And you will have this nature, in a certain sense, new compatibility condition. Whenever you take a free dynamic index set in J, and any point in this domain, you get that the derivatives are always rho moderated, but you see here J epsilon. So you are moving from one section to the other. And here you have this compatibility condition. Here J epsilon, and here H epsilon. Okay? And finally, we see that this family satisfies dynamic compatibility condition on the cover if it satisfies this dynamic compatibility condition for every functioning compact set contains in X. So we have this theorem that states essentially if on the set X of generalized number, we have that Fj satisfy, Uj is a strongly internal set, Fj satisfies the dynamic compatibility condition, then you can glue together all this generalized function, you get a new generalized function. Very important, the dynamic compatibility condition is stronger than the classical one. Is a necessary condition if you assume that the section glued together into a new generalized function. And so our first question, which connects this theorem to topos theory, is that whether this dynamic compatibility condition is a particular case of general abstract notion or sheaf or not. So we first introduced the category of global families. A global family is essentially is a non-empty family, arbitrary index in some J, of strongly internal set. Each one contains in a fixed depending on the family, R tilde U. So the dimension depends on this family, coming family. And we say the two maps between a global family is a function, it's a pair of a family and an alpha. Alpha takes any point in the index set of the first family into a point in the second index set of the second family, and it's called indeed the reparameterization. And Fj is a generalized function defined on strongly internal set, and you see here it takes a Uj into V alpha J. Okay, so we transform the first index J into an H index alpha using alpha, and we get as function. And this union means a functioning compact exhaustion. What are composition and identities in this category? If we have a tripole of this form, of course we can take the first Fj goes from Uj to V alpha J because you have a reparameterization alpha. Then you take the second reparameterization beta in the second map. So you get from this index set to this index set, and you have the composition of this reparameterization family. So it is natural to define composition and identity in this way. And indeed you get the category, and very important that the category of strong internal set and generalized function is contained in the category of global family. Then we introduce a coverage of global functions, which is an arrow of the category of global family, where delta is a surjective map. The family Ij now is given by a German function given by inclusion, and we have this covering property. We have this way coverage on the category of global functions, so we have a concrete site, and so we can introduce the Grothendieck topos by considering the sheaf on this concrete site, the Grothendieck topos of generalized function. And the dynamic compatibility condition is absolutely the key property to prove that this functor is a concrete sheaf on this concrete side. So it is an element of the topos. Okay. And so this, in a certain kind, we had two aims in arriving at this result. The first was to say, okay, is our dynamic compatibility condition a particular case of the abstract notion of sheaf? And we can say yes, it is. And the second one is to construct a framework where we can talk freely about function spaces, that is to use the Cartesian closeness. Okay? And indeed, this was the topic of a project proposal of FWF. FWF is the National Science Foundation in Austria, and together with several Japanese universities. And the idea is to develop a real interdisciplinary project, because I introduced the knowledge of generalized function, they introduced the knowledge of algebraic topology, and they don't know essentially anything about generalized function. I don't know almost anything about algebraic topology, so it's real interdisciplinary. We have to make a lot of exchanging. And the main idea is to make a differential homotopy theory, that is homotopy theory, but where continuous functions are embedded as GSF, so they are managed as if they were smooth functions. And on the other hand, also synthetic differential, possibly non-smooth synthetic differential geometry using this kind of generalized function. And so I want to talk a little bit about the ideas of this project. I hope it will be a project in the next few months. First of all, the Japanese guys want to work in difflogical spaces and homotopy theory for difflogical spaces. Difflogical space is a concrete sheaf on the concrete site, it's called Fourier site of smooth function. That is, you take open set in Rn, these are a concrete sheaf, and you can take a concrete, this is a concrete site. And essentially, concrete sheaf means that you have a support set, you have a family of functions defined on open set in some Rn with values in this support set. And these are called plots. They are closed. The plots are closed with respect to constant function, with respect to composition on the left, and with respect to a natural gluing property, sheaf property. Okay. So we first want to try a definition. This is already possible. Generalized difflogical space as a concrete sheaf on the concrete site of the Grothendieck topos of a generalized function. But on the other hand, we want to try to find a characterization of concrete sheaf over this site, aiming to arrive at a definition which is close as possible to the usual definition of difflogical space, that is the support set with some kind of sheaf property, probably related to the dynamic compatibility condition. Then understand what are generalized maps between these generalized difflogical spaces. And so since the Fourier site of ordinary smooth function is contained in strong internal set and generalized function, this is contained in topos, we want to prove that the difflogical spaces are also contained in the topos, and this would imply that also manifolds are contained in the topos. And so we can start talking also about manifolds. The second point, another point, so there are several points in the project, is to define the extension of every difflogical space, that is, you can think of manifolds. So exactly as the real fields has been extended using infinitesimal and infinite and other kind of dynamic number into R tilde, we want to extend any difflogical space, in particular any manifolds, adding these non-Archimedean points. This is important because if you restrict your generalized function only to classical static real number, you trivialize all the non-Archimedean information. So delta is 0, okay? And H does not satisfy the intermediate zero theorem. So it's important. A possible definition is to consider all the open set over any difflogical space, and then take the strong internal set generated by this standard open set, and they then take the colimit in the topos, and this is a possible definition of the extension. That is, we take this open set, and so the colimit of this open set, standard open set, defines is isomorphic to the difflogical space, and then we extend this open set, and then we glue together with the colimit in the topos. We hope to get a very good notion of this extension. This is also another idea to define an extension functor. And using this extension functor, we want to study its preservation properties. So preservation, counter image, union, intersection, some kind of preservation of complements, classical or intuitionistic complements. subspaces, quotients, and so on, exponential object. A difficult part is to define the standard part functor. That is, the extension functor goes from here into the topos. The standard part function can be some kind of adjoint of this, but the problem is that in our non-Archimedean setting, not all the point has a standard part. Standard part means, for example, a generalized number has a standard part if this limit for epsilon going to 0 exists and it is a standard point in Rn. This is called the standard part of this point. This means that it is dynamic, but for epsilon going to 0 converges to some points. This is the standard part, but not all the generalized number has a standard part. You can take a point going to infinity or a point that continues oscillating and so on. So it's a difficult part. And indeed, our theory is strongly constructed, not on the formal point of view, but from an informal point of view. And the standard part is the most non-constructive part on non-standard analysis.
Sorry, can I ask you?
Yeah, of course.
So you mentioned intuitionistic component with the theory.
Sorry, here?
What do you mean by impede?
The interior, sorry. Interior, yeah, sorry. This is for that I told in intuitionistic negation, because you have to start from an open set and arrive to an open set after taking the negation. Okay. And in this second we can realize, actually the idea was of Professor Shimakawa, differential homotopy theory in using generalized function in these settings. For example, two basic but I think intuitively important steps are that we want to prove that the n cube, the n simplex, and the n ball are actually isomorphic if you take a generalized function. Of course, you must have singularity points in this isomorphism, but it's not a problem for this kind of generalized function. And we already proved, for example, that there is a GSF diffeomorphism between the closure, the ball, the closed ball, and the cube. And here you have a singularity. Okay. And so we can try to generalize a homotopy theory that is treating continuous function by taking derivatives. So if they were smooth functions, so taking any kind of derivatives, all the classical theorem for smooth function. The other part of the project concerned syntactic differential geometry. Probably each one of you knows the syntactic differential. What is the syntactic differential geometry? At least I hope. But here is a very quick summarize. Syntactic differential geometry uses a lot of topos theory and uses a non-Archimedean language, but of nilpotent infinitesimal. Nilpotent infinitesimal means that you have, in a certain sense, different from zero number. You can ask me why, in a certain sense, but such that it is so small that h to the n is equal to 0. Okay? These are actually, they're not crazy numbers. These are actually the infinitesimal used by Einstein. Okay? If you look at the book about the Brownian motion, he uses exactly this kind of infinitesimal, informally, of course. And the idea of syntactic differential geometry is to formalize coordinate-free notion of differential geometry exactly as they were invented by Lee, Cartan, Grassmann, and the other guys. And you can see the book of Koch, Lavendom, Murdoch, Reyes, which needs topos in intuitionistic logic. Okay, but you can also take a look at paper of Wu and myself about Fermat reals, where you have a framework and then other quasi-topos, but in classical logic. Okay. Very important. In syntactic differential geometry, I think it is a wonderful theory, even if it is in intuitionistic logic, where you can synthetically consider tangent vectors, essentially all the results, a classical result of differential geometry, and this holds not only in manifolds, finite dimensional manifolds, but also in spaces of smooth mappings between two manifolds without any compactness condition on the domain. Okay, so not necessary. In general, this is not a manifold. And in synthetic differential geometry, you can have this kind of result. So it's very important. Fluid dynamics lives here. Okay, yeah. So we can introduce a language of nilpotent infinitesimal also in our ring of Robinson-Colombeau. We say we have a family, so this is in developing, okay? So a lot of things. These are already all proved, but we are a lot of open problems, okay? So we introduce a new family of languages depending on this J. J is any real number, positive real number. We say that these two generalized numbers are equal up to jth order infinitesimal if this distance is a big O of rho epsilon to 1 over J. And we introduce with this language, with this equality, the set of all the infinitesimal of kth order, the set of generalized numbers such that for this equality, the k plus 1 power is exactly equal to 0 with respect to this equality. This is the set of all the infinitesimal, nilpotent infinitesimal. Very important if you have why this parameter, because if you have that two generalized numbers are equal for any j sufficiently small at the j level, then they are equal as Robinson-Colombeau generalized number. And this is the key point, the so-called Cocklovier axiom in synthetic differential geometry. We can prove it. This is has been already proved, and it also for generalized smooth function. So also with infinite derivatives. Okay, not only smooth function. So also with continuous function, embedded continuous function, distribution, whatever you want. That is using nilpotent infinitesimal. This is the set of all the nilpotent infinitesimal of order n. You can write the Taylor formula without any remainder. This means that any generalized smooth function is exactly equal with respect to this equality to a polynomial. Okay? And this is why Einstein used this kind of infinitesimal. You can simplify your calculation a lot, of course. Okay? Simply saying, by a physicist point of view, since h is very small. Okay, and you write equal. Of course, this is not. But you can see the usual teaching of the wave and the heat equation at the first years of mathematics is full of this kind of infinitesimal and of we first write approximately equal, and then magically this approximately equal becomes equal without saying anything to the student, because I don't know where this approximately equal becomes equal. Okay, so idea for generalized synthetic differential geometry in these settings. So in the setting of generalized smooth function and generalized number. So a tangent vector for this equality is an arrow, so it's a generalized function, this topos, of the form defining for first order infinitesimal for this equality with values in x and such that t of 0 is equal to x. So intuitively, it is an infinitesimal line starting from 0 and traced on the space x. Okay? So no needs of coordinates. Of course, multiplication by finite scalar. Here we have a very deep difference with respect to classical synthetic differential geometry, because we don't have only finite scalars, but we have also infinite scalars. So we have to distinguish between finite and infinite, but the product of tangent vector and the finite scalar is simply by stretching the speed of this infinitesimal path. Okay? Using Cartesian closeness of the topos, you can define a tangent vector, a vector field as a tangent vector to the identity of the space of all the transformation of x tilde into itself, or in the classical way. And these are equivalent using Cartesian closeness. Very important in infinitesimal linear space, some kind of substitution of manifolds, but that holds also in infinite dimensional spaces, like spaces of smooth function. In infinitesimal linear space, essentially the idea is if you start from n tangent vector at the same point, then there exists one and only one parallelogram generated by this vector and having as sides this vector. This means that if you want to define the sum, simply you take the parallelogram exactly generated by two vectors and you take the diagonal. Once again, these are not my ideas. These are all from synthetic differential geometry, okay? And originally from
I know that this is not perfectly rigorous, but I hope that in the future they will arrive at the formalization of this idea, this way, not in another way. Okay? And so infinitesimal linear spaces, I hope that always includes extension of manifolds, but also this space, and now we use once again the topos, and this includes a lot also of generalized function. We can, I hope personally, to have some possibility to define differential forms using the original Grassmann idea, that is, using infinitesimal p vector at that point. Okay, I finished. This is my website. Here you can find all the paper, also the paper about format reals, if you want to see something about synthetic geometry and classical logic, but also if you are interested into mathematical theory of complex systems and ideas about the application to artificial general intelligence, you can find everything.